Hello again. Welcome to Basics of Finite Element Analysis Part 1. This is the first week and today is the second lecture of this course. In the last lecture we had covered a very broad based overview of the course, and today we will further elaborate on the concept of finite element analysis by a very simple numerical experiment or an example. So, what we are going to do today is calculate the area under a curve and somehow apply what we learned through this example to finite element analysis method. So, suppose I have a function. So, this is my x axis, that is my y axis, and this is my y equals some function of x. Okay? And in this case f x is equal to constant some c. So, the value of this f x is c as x is varying, and what I am interested in is to compute this area under the function. Okay. So, because f x is equal to c, we know that if I integrate f x with respect to dx and if I evaluate the values of that integral between the limits x 1 and x 2, I will be able to compute this area. So, that is what we will do. We will do, so what it comes down to is area. So, this area is equal to integral from x 1 to x 2 f x dx, and that because f x is c, so it is c times dx x 1 to x 2, and this is equal to c times x 2 minus x 1. Okay. So, this x 2 minus x 1 is the width of this rectangle and c is the height of this rectangle. And this is a very trivial example, but this is how I wanted to begin with. So, what I have explained is that if you have a simple function, you can integrate it in a closed form way and you can calculate this area. Okay. And your calculation will be accurate and the error will be 0. So, this is an exact solution when we are trying to calculate the area. Now, let us look at another example. Oh, by the way, before I go to the second example, a couple of things. So, here the region of our interest in which under which we wanted to calculate area was what? X 1 to x 2. So, this x 1 to x 2 is the domain. In this case, domain is one dimensional in nature because it involves only variation of x. There could be situations where domain could be two dimensional in nature. Suppose I want to calculate the volume which is covered by, let us say, my hand and this baseline surface. So, there the domain could be, that is a two dimensional surface, and so there the domain is a 2D thing, here domain is 1D. Similarly, I could have a 3-dimensional domain, so that is there. So, now moving on and going back, I have another function f x. So, this is my y axis, x axis, but it is very complicated. Okay. It is very complicated, and I have to find the area between x 1 and let us say x 2. So, this is the area I am interested in. Now, if this function was easy to integrate, I would have an expression. So, this is my function f x. If this function was easy to integrate, then I would just straight away integrate it, and I will do a integration under limits x1 to x2, and I will get a exact solution. But here first thing is I do not know what is the expression for this function, and the second thing is even if I knew it may be a very complicated function, so I may not be able to integrate it. So then I use a numerical approach. Okay. So what I do is I break this area into small, I break it into small slices, and this is exactly what we do when we are trying to integrate differential equations also. It is a more complicated process, but the philosophy is same. So I break this overall area which we are trying to calculate into small slices, okay. And let us say this slice is S1, this slice is S2, this slice is S3, and so on and so forth, okay. So my total area here also our domain is x1 to x2, it is a one dimensional domain. Total area will be area of S1 plus area of S2 plus area of Sn. So suppose I break it up into n slices, then the total area will be the area of each individual slices. So now if I have a way to figure out what is the area of each slice, then I can calculate this. So what is the area of first slice? Now I can calculate the area of first slice in several ways. So approach 1. Approach 1. Here what I do is I assume that the height of this, so let us put some A, B, C, D. So what we are trying to figure out is area of ABCD, and our first approach is that the height of this ABCD is constant, okay. So in that case height of ABCD is constant. Suppose I assume that. If that is the case and it is AB, so let us say this value of AB is y1, then area of ABCD is equal to what? Y1 times x. So let us say this distance is delta x, then y1 times delta x, okay. If the height of this ABCD is constant, height means the distance in the y direction, okay, the distance in the y direction is constant, then it will be y1 times delta x. Is this clear? So basically what I am saying is this, that this complicated shape ABCD is not that, but I can approximate it as something like this, right. So effectively what I have calculated is not ABCD, but the area ABED. Do you understand? Okay. And in this case what is the error? The error will be BE and C, area of BE and C, that will be the error, okay. This is my first approach. Then I will say okay, maybe I can have a better approach. Approach 2. So second approach is that I do not treat ABCD as a rectangle, but I treat it as a trapezoid. So if I treat it as a trapezoid, then I draw a straight line between B and C, right, and then in this case suppose the height at point C is y2, then area of A, B, C, D is y1 plus y2 by 2 times delta x. Okay. So, this is the second approach. I can have a third approach. I will say the third approach could be that I will say, okay, so first approach is that I treat this complicated shape as just a simple rectangle. Area error is large and it equals the area of B, E and C. Second approach is I treat it as a trapezoid. In that case, the area is, the error is this region between the two green lines, you know. I do not want to shade it right now because I will draw another curve there. And I can have a third approach and I will say, okay, in the third approach, this transition of height between B and C, see right now in approach 2, the transition of height between B and C is linear. I will say, okay, it is not linear, but it is some quadratic in nature. So, my line will be like this, okay, and I say that this blue line is a quadratic curve. Okay. So, now if I know that this is a quadratic curve, then I know the equation for the quadratic curve, right, and I can again calculate. So, basically if the moment I say it is a quadratic curve, it is not a straight, see in first case it was a horizontal line, second case it was a straight inclined line, third case it is a quadratic curve. So, in approach 3, area of ABCD is area under quadratic curve. So, using principles of geometry I can develop the equation for this quadratic curve easily, right, and then I can integrate that quadratic equation between limits x1 and x1 plus delta x and I can get that area. So, what happened to my error? It went down further. Then I will say that okay, approach 4 could be that it is not a quadratic curve, it is a cubic curve. So, I can make this transition between B and C more and more accurate or closer to reality if I keep on increasing the number of polynomials which capture the transition from B to C more and more accurately. Okay. So, this is what happens in finite element analysis also. So, we can take either of those estimates. The first estimate is approach 1 where the height is constant, second approach is where height is linearly increasing, third is it is quadratically increasing, fourth could be it is cubically increasing, and in each step of sophistication I am getting a more and more accurate solution, more and more accurate solution for the area for this rectangle ABCD. And similarly I can calculate areas for the second slice. Again I can have different approaches, approach A, B, C, D, right. Then I can have for the third slice. So, whatever approach I think is most accurate, I can pick up that approach and I can then compute area of each of these slices, add up all the areas of these slices and get the final area under the curve. Okay. So, in this context I would like to make couple of points. First, as delta x goes to 0, error goes to 0 also. It does not matter whether it is a constant curve or it is a inclined curve or it is a, this is one thing. So, this is one, which means that if the size of delta x is dx, which is infinitesimally small, infinitesimally small, then I will have 0 error. Agreed? This is one thing. But what does that mean? If I have infinitesimally small size of the slice, it will mean that I will have to do these computations infinite number of times. Okay. So, but in finite element method, the size of the slice, and now we will use this term called element. So, here what we were doing is that we have broken this line which is for fx into slices, I can call it, or I can call them as elements. Okay, I can call them as elements. So, if the size of the element goes to 0, I have to do that computation infinite number of times, which is physically not possible. So, what I do is that I reduce the size to a significantly small number, but it is still not infinitesimally small. So, I still have not infinite number of elements, but finite number of elements. Okay. That is where the term finite element comes into picture, that the size is not extremely small and vanishingly small, but it is finite in size, and also the number of elements is finite. So, this is one. So, as delta x approaches 0, my error goes to 0. This is one thing. The second one is, as our approach, see, we in first approach we assumed that height was constant. In second approach we said height was linearly varying. In third approach we said that height was quadratically varying. So, as our approach becomes more sophisticated, and this is a general thing, becomes more sophisticated, error goes to 0. Okay. This transition from point B to C, right, in first approach there was no transition, it was constant. In second approach it was linear transition. In third approach it was quadratic transition. And this function which helps in understanding the transition, so here it is a constant function in first approach, right, constant function. Here it is a linear function in approach 2. In third it is a quadratic function. These functions which explain how variables are changing over an element, not across elements, over an element, they are known as shape functions. Okay, shape functions. Because they help us understand the shape of the transitions from point A to point B on an element. Now, these functions which I have plotted in this line are one dimensional, because they are only functions of x. If you have a plate or a shell, it could be a 2-dimensional function. If you have a solid object, it could be a 3-dimensional function. Okay. So, these functions could be 1D, 2D or 3D, but they help us understand that within an element how is u, suppose you are trying to capture u, how is u changing from one point to other, is it linear transition, is it a quadratic transition, is it constant, is it cubic. Okay. So, that is there. So, these are known as shape functions. And fourth is that these small slices which we called slices initially, this is what is element. This is what is an element. These elements have, at least in case of a linear 1D element, it has 2 endpoints, right, it has 2 endpoints, but they could have internal points also, Suppose, suppose you have a quadratic function, then to see how the function is changing over an element, you have to develop a quadratic expression, right. To define a line you need 2 points, to define a straight line you need 2 points. So, this linear function, for this you need the values of this green line fx only at point B and C, right. But to define a quadratic function which transits from B to C, you need 3 values, you need 3 values. So, for a quadratic function which is one dimensional in nature, you have to get value at one endpoint, you have to get value at other endpoint, and you also have to get a value at somewhere in between, because what is a quadratic function? It is ax square plus bx plus c. So, to find a, b and c, you need values of that function at 3 points. Similarly, for a line, linear line, it is y is equal to ax plus b. To calculate values of a and b, you need values at the endpoints. But for quadratic, you not only need the value of the function at endpoint, but also the value at maybe midpoint or somewhere in between, at somewhere in between. Okay. So elements have nodes where we are interested in finding the values at ends only for linear elements, and they also have nodes at ends and in between for higher order elements. Okay, is this clear? Now, how do we use all this theory? We will explain it in the next lecture. But what I wanted to impress upon you is that the accuracy of our, when we are trying to calculate the area, we have seen in this case, it depends on 2 parameters. The first parameter is how thin each slice is, or how small each element is. The more small we make, the better we get in terms of reducing the error. The second way of reducing the error is that not only we may make the slice small, but we also pick up a better transition between 2 endpoints of the unknown variable. Okay. So a higher order shape function. Another term for this shape function is interpolation function. So, in this class I will use shape function and interpolation function interchangeably. They are known as interpolation function because they help us interpolate the value of unknowns between 2 nodes. Okay. If I know the function, using that function I can interpolate the value of the unknown between 2 nodes using interpolation methods. So, they are known as shape functions or interpolation functions. Some people also call them as basis functions. So, these are, so if we use higher order shape functions, that also helps us increase the accuracy. If we reduce the size of the element, we have seen that also helps us reduce the error and increase the accuracy. These are 2 ways to increase accuracy of, at least in context of this example, the area under a curve. We will extend the same thing in several other subsequent lectures we will use the same idea to when we are trying to solve differential equations. Thank you.